So, today we will discuss on materials which are used for MEMS and microsensor devices. So, you know materials are the fundamental things or basic things based on which we develop various kinds of sensors. We are exploiting the properties of materials, and the materials are of different class, and all those classes little bit I will discuss in today's lectures. So, the materials which are used for MEMS are basically from different group. Some group belong to the metals or metal alloys, some group of metals belongs to semiconductor, particularly silicon, and metals and metal alloys other than those sometimes we use some ceramic materials also and polymers material. So, these are the four class of materials which are used for making various kinds of microsensors. Now, let us concentrate first on metal and metal alloys for MEMS. So, we use thick metal films for those devices which are used for structural materials for final sensors, and sometimes it is also used as a mold which is inserted into the polymer on ceramic micromolding. What do you mean by micromolding and what are the molds, that I will discuss during the micromachining class. This is a technique by which you can make the mold or micromolds, that is in chapter micromachining. Now, this other than this micromolding, there are other techniques which are mainly micro electroplating or photoforming. These are used to build thick metal film structure for different components of the microsystems or MEMS devices. Electroplating is another technique which is used for making thick metal films. Thick means I want to say several microns, maybe 20 micron, 30 micron, 40 micron, in that range. If you want to deposit the more than tens of microns, then conventional the thin film evaporation technique or sputtering technique cannot help. With that technique you can get films of the order of maximum 2 to 3 micron, and if you want more than that 10 microns, 15 microns, 20 microns like that, then you have to adopt certain techniques. Those are mainly the CVD techniques and the electroplating technique. Electroplating technique is getting lot of importance nowadays, because this particular technique is a low temperature process where the chemical techniques are used, and basically it is a electrolysis of some chemical solution, and you have to have a cathode and an anode, and you have to supply some current through that electrolytic cell, so that the chemical electrolyte will decompose, and some part will be the metal, and that metal will be deposited on cathode. So, that is the basic principle, and with that principle we can have the metals of thicker films, for example, gold, nickel, copper, chromium, those are deposited by electroplating techniques, and various applications are there for the electroplating of gold, nickel and copper. Copper material particularly is used nowadays in VLSI also for interconnects, because of very low resistivity of the copper material. So, conventional techniques which are used for VLSI metallization are mainly the thin film evaporation. There are certain problems because of which copper cannot be evaporated in vacuum by resistive, or electron beam evaporation is not possible. So, electroplating is the only choice by which we can get the copper film on silicon or silicon dioxide, which is used for interconnects in VLSI. But in case of MEMS, the materials used in electroplating are mainly chromium and gold, and chromium is used for adhesion of the gold film with the silicon or silicon dioxide substrate. This is a buffer layer, and basic material used for those purpose is gold. Now, these are the techniques. Another is a 3D stainless steel micro parts by photoforming. So, the stainless steel materials are also used for making 3D structure. So, you have seen in my last lecture lot of application where 3D micro parts are used in many actuators or many microsystems. So, those which are made of steel that cannot be evaporated, that cannot be electroplated, that is formed by photoforming is another technique. So, that photoforming basic principles how it is being made, that I will discuss in separate lecture. The third combination is a metal alloy which are cobalt, nickel, manganese thin films, which are basically magnetic material. This alloy cobalt, nickel, manganese is used for permanent magnetic materials for magnetic actuation. So, sensors and actuators, some parts are sensor and some parts are actuated, and actuator principles are various kinds of principles are used for actuation. One such principle is magnetic actuation, and for magnetic actuation you need magnetic material, and those magnetic material, one of the important material is copper, nickel, manganese alloy. So, titanium and nickel are used for safe memory application. So, this has tremendous application in MEMS and MEMS and actuators also, and this is used sometimes for sensing and actuating also, and in short it is known as SMA, safe memory alloy. And electroplating of nickel and iron permalloy on silicon for magnetic MEMS is also getting importance nowadays. So, these are the various kinds of metals and their alloys are which are used for microsensors devices. Now, next I will discuss on polymer, and polymers are extensively used nowadays as both structural and functional materials for micro devices and MEMS. Polymer can be used as a structural as well as it can be used as a functional material also, and I will show you some table which properties are used for making functional layer or functional device, and which property of polymers are used for structural device. I will show you in the next slide. Now, the main properties used for polymers are elasticity, optical properties of polymer, biocompatibility of the polymers. These are the main advantages of the polymers. Because of that, it can be used as a structural materials for MEMS. Now, polymer strain gauges and capacitors serve as sensing elements of piezoresistive and capacitive microsensors. Piezoresistive and capacitive microsensor, some of the applications I mentioned in last lecture, that is in the pressure sensor, and there also you can use the polymer material and it can used as a strain gauge. Electrostatic polymer microactuators can be formed from polyimide. Polyimide is a one class of polymer. It has got electrostatic properties and it is used for making microactuators. Polyimide based ferrite magnetic composites for magnetic microactuators is another application. Polymer as electronic material, and that electronic material like semiconductor, silicon, germanium. Similarly, polymer can be used as electronic material because nowadays polymer transistor has come up and FET has been successfully fabricated using polymer, and people are thinking polymer can be used for active device fabrication also, so that both passive and active components and MEMS components can be integrated together, and as a whole total will be known as polymer MEMS. So, I will take one separate lecture on polymer MEMS in future. Single crystal polymer is also possible. Earlier people could not think that single crystal is basically the properties of semiconductor materials, and here you can have polymer as a single crystal, because you can have certain chain and some series of chains, polymer chains are created, and those chains are regularly repeated in a particular material. If you arrange those chains in a regular way, then it will work as a crystal. So, that is also research is going on how to get good quality polymer crystal also. Now, this table shows the properties of the polymers and its fabrication techniques and used in which case it is used as a MEMS devices. Now, some of the polymer names I am showing here: polyamide, parylene C, PMMA. PMMA is basically used as a photoresist material also, polymethyl methacrylate, polyester, polycarbonate. And polyamide, its fabrication process is coating technique, parylene C is also coating technique, PMMA is used, fabrication is Liga technique, polyester is casting technique, and polycarbonate hot embossing. So, these are the fabrication process. And polyamide material, when it is used, the elasticity property of polyamide is used for those devices. Similarly, in case of parylene C, vapor barrier property is utilized. For PMMA, elasticity and optical properties are utilized. In case of polyester, elasticity property is utilized, and polycarbonate, both elasticity and optical properties are utilized. So, when you use polymer as functional material, then we use some functional property, and those functional properties are piezoelectricity, conductivity, and electrostaticity. So, these are the functional properties, and its main applications are either sensor or actuators, and the names of the polymers used for sensors and actuator and used as functional and employing the functional properties are PVDF, polypyrrole, and fluorosilicon silicon, and polyurethane. These are the polymer materials which are being used nowadays in different kinds of the micro sensors. Now, come to the ceramic materials for MEMS. So, we discussed on metals, metal alloys, then we discussed on polymers. Now, we will discuss on ceramic materials. So, ceramics are inorganic materials that consist of metallic and non-metallic elements chemically bonded together. That is the definition of ceramics. And the materials used for ceramic materials used in MEMS are aluminum oxide, silicon dioxide, silicon nitride, sodium chloride, calcium fluoride, and YBa2CU3O6. So, this is a new the ceramic material which have started using in case of MEMS devices. Ceramic pressure microsensor for high temperature environment, in which area ceramic materials are promising, particularly two areas, one is high temperature and is harsh environment. So, in high temperature and harsh environment, you cannot use the metallic MEMS, because most of the metal at that high temperature will become softened and its property will be lost. Another thing is semiconductor material, if you use for at a high temperature, then problem is semiconductor property is highly dependent on the temperature. So, there if we use piezoresistive property, then at high temperature that property will change. So, the change of piezo resistance due to the strain and as well as due to the temperature change will combine together, and you cannot separate one each other. So, those are the problems at very high temperature. So, there the normal metal or polymer or you can semiconductors are not promising. There we have to go for certain ceramic materials which can withstand very high temperature, and other is in a harsh environment, that is also another application of ceramics. So, silicon carbide, a promising material for MEMS for harsh environment. Silicon carbide is a new is a very important material nowadays used in case of the optical devices in VLSI also. Other promising functional ceramics are zinc oxide and PZD, lead, zirconate and titanate, that is PZD and zinc oxide. These two materials are extensively used nowadays as the functional material for MEMS. Fabrication of ceramic MEMS, techniques used are screen printing, tape lamination, micro molding, sol gel and MSL. MSL stands for micro stereolithography. So, micro stereolithography technique is used to get 3D structure in polymer, in ceramics, and in sometimes in case of the composite materials also. So, that the MSL technique is a special technique which is not being used in VLSI, but is extensively used in MEMS, and detail I will discuss the microstereolithography technique in a separate lecture. Now, let us come on to composite MEMS material. Composite materials are basically combination of materials from different groups, which I mentioned 4 groups is a metal, semiconductor, polymer and ceramic. Of these 4 groups, if we combine materials from different group to obtain the desired material characteristics, then it is known as a composite material. And lot of research is going on composite materials to achieve various specific properties. If we combine the metal with ceramic, you can combine polymer, ceramic and metal. Sometimes semiconductor materials are also used to have some composite things which has got unique properties for unique application. So, these materials are used as passive materials in microsensors and MEMS. Smart materials when used as active materials in MEMS. Smart mean it will have certain unique properties which does not have in case of it does not have in metal, semiconductor, ceramic and polymer. So, that is why it is known as smart. So, it is specific property you can create by combining materials in different proportion. Electroactive polymers, example is polypyrrole, that is used as chemoresistive sensors in an electronic nose. So, electronic nose on device which can sense different gases, different stink, that is known as the electronic nose, and there the polypyrrole material is one is electroactive polymer. So, that is used in those cases. So, now these are the different classes of materials used in case of MEMS. Now, let us discuss little bit on the semiconductor. Semiconductor mostly we use silicon. So, there silicon is a single crystal silicon. So, in that respect now I will discuss sometime on the some material properties and some definitions. Already you know some definitions relating to the crystal, relating to the properties of silicon, relating to mechanical properties of the materials. Even then I will just further spend some time on the basic definitions which are very much used when you are going for designing certain sensors. So, crystal, there are 3 kind of material: crystalline, polycrystalline and amorphous. There is a difference between the crystal and polycrystal, crystal and amorphous material, and amorphous and polycrystal. You should not confuse yourself between polycrystalline and amorphous. Crystalline is known because it will have long range regular order and a periodic arrangements of atoms in a crystal, and that periodic arrangement of atoms, these are known as the lattice, and all the atoms in a crystal are located in the lattice points, and the distance between the lattice points is known as the lattice constant. So, this periodic nature in a long range will maintain, that is the single crystal silicon. But if you look into the polycrystalline, then it is not long range. In a short range, locally the regularity is maintained, the structure is maintained, but over the long range it is not maintained. Okay. So, that is polycrystalline, or the microcrystal you can say. In a small region it is crystalline, but over all throughout the whole bulk of the material it is not crystalline, it is a polycrystalline. On the other hand, the amorphous, there is no regularity between the crystal lattice structure, is a highly irregular, and the crystal are or atoms inside the crystal are oriented or are placed in different direction. So, in the haphazard direction, so it is known as amorphous material. One example is, if you evaporate certain metal film on a single crystal silicon substrate, this film is amorphous film. For example, if you implant silicon by certain ion in ion implanter, the region where the implanted species will locate will sit, those regions initially it will be highly amorphous. Later on you have to do the sintering or annealing, so that again you will get back the regular silicon single crystal structure. So, those are the amorphous examples. Polycrystalline is also an important material which is used as sacrificial layer, sometimes structural layer in case of MEMS. So, that is achieved by CVD technique or sometimes by ion beam deposition also you can get the polycrystalline material. Now, in these crystals a set of integers known as HKL, those are also called Miller indices, is used to identify a set of planes or directions in a crystal. So, when you will be using that silicon, sometime you will see that is 100 silicon, 111 silicon or 110 silicon, different crystal planes are also cited along with the single crystal silicon. And those planes are, how to define those planes? Those planes are defined with the help of the integers which are Miller indices. For example, silicon basic is the cubic crystal structure. You can see the x, y and z, these 3 axes, and this is a cubic crystal structure. Now, here this, if a plane which is perpendicular, say this is x, this is say y, this is z. So, a plane on the x axis here and parallel to the say y and z plane. So, this plane particularly is known as 100 plane. Okay. So, in this direction you have taken h, for example, you have taken 1 and KL 0 and 0. Similarly, this plane here in the top is known as 0 0 1, and on the other hand this plane in this surface here is known as 0 1 0. Okay. So, in this way if you take a plane like that, that means from this is the origin, from here you have taken 1, from here you have taken 1. So, and this is a parallel to this axis, then this plane is known as 110 plane. Similarly, here you can, this diagram you can see. So, this here is 1, here is 1 and here is 1. If you take a plane along this, so like this, so it is known as 111 plane. Now, the crystal plane, how can you define it? So, it is defined from the manufacturer will crystal, he will make the slice with certain direction, accordingly the crystal cut, this is known as a crystal in which plane you are cutting the slicing the crystal, that is either 111, 100 and 001 or 110 like that. And different crystal plane will have different atomic densities, because the silicon atoms are placed in a certain manner inside the crystal. So, if you cut the plane in different parallel to certain axis, so in that particular plane the number density of the silicon atoms will not be the same in all the directions. Okay. Now, one point is also important, how do you identify a crystal is 111 or 100 or 001, how do you identify? So, one technique is by X-ray technique, but always in the laboratory you will not have the X-ray techniques. So, there are certain nomenclature is followed everywhere by the manufacturer of silicon wafers. So, accordingly by seeing a silicon wafer we can identify whether the silicon crystal slice is 111 direction or 100 direction or 110 direction. So, here are some figures you can see. So, here you can see this they cut here, this is known as a primary flat. Okay. This is a circular thing. So, here is a flat which is known as primary flat, and here is another flat which is known as secondary flat. Now, this is the center of this slice. So, from center with the primary flat and the secondary flat, the angle is 45 degrees maintained. Now, if a primary flat and secondary flat is made like this, then this silicon slice is 111 n type. Similarly, if only this primary flat is there, then it is known as 111 p type. So, those flats are made from the from the manufacturer. So, their company will make those flats. So, accordingly by seeing a silicon wafer you will identify this is p type 111, this is n type 100, sorry 111. So, in the other hand, if there is a flat here and in a 180 degree there is secondary flat, the distinction between primary and secondary is the primary flat you can see is longer than the secondary flat. Now, here if you 180 degree direction there are two flats, then it is known as 100 n type silicon wafer. Similarly, if there is a 90 degree orientation of the primary flat and secondary flat, then it is known as 100 p type silicon wafer. So, in case of the MEMS device or even in VLSI devices, so normal wafers we use nowadays is 100 silicon wafer mainly. There are certain advantages of that. Main advantage is that the 100 silicon can be cut into small pieces regular way, because whatever devices you made either is a VLSI chip or MEMS, at the end you have to separate the chips, you have to break the chips. So, 100 wafer can be broken in a regular fashion and you can have the small pieces of dies, but in 111 you cannot break in regularly, you have to use some diamond saw, and even then some of the pieces will break in different angles. So, some of the pieces you can lose in this way. So, that is why 100 is a popular oriented crystal that is used, but for certain specific application in MEMS, so we also use say 110 as well as 111 oriented silicon wafers. This is the crystal structure of the single crystal silicon, that is you can see the is a bond this is basically a diamond cubic structure and bonded with 4 covalent bonds, and it belongs to more general zinc blend structure. So, a face center cubic. So, this is a cube structure, each face there is also a single crystal silicon. This is silicon, silicon, silicon and silicon, and at the face also another is known as a face center cubic structure. This is the basic structure of crystalline silicon. Now, we will discuss something on mechanical properties of materials, because MEMS is is a micro electromechanical system. So, mechanical properties and its definitions we should know. So, although some definitions are known to you, again I will recapitulate those definitions, I will remind those definitions, because when you are going to design it is very important to know or to aware those definitions accurately. Okay. Now, some is a axial stress and strain and some are known as shear stress and strain. So, what is the difference between axial stress and strain and other is shear stress and strain. So, in this slide axial stress and strains is described. For example, this is a bar, rectangular bar. Now, if we apply force axially or normal to the surface, because the force is applied normal to this surface and along the axis the force is applied. So, now if we apply the force in axial direction, so its length has been increased in this direction as well as in this direction, but we assume that diameter is not changed. In ideal condition, let us assume the diameter is not changed, but length is only changed. Okay. Now, this is known as the axial strain. If we apply stress only on perpendicular surface along the axis, then diameter is not changing, but length is changing, then it is known as we applied axial stress and strain is axial. The axial stress is defined as the force per unit area, that is Newton per meter square. The F is a Newton and per unit area is meter square, and normal strain which is given by you see epsilon is equal to delta L. Delta L, what is delta L? This is a change in the length. This is the L naught and total change is the L naught plus delta L. So, how much increase in the length direction, that is the delta L, divided by L is known as normal strain. and Young's modulus or elastic modulus is defined by stress by strain, which is sigma by epsilon. That is the Young's modulus or elastic modulus is an important mechanical property which is will be used for designing any micromechanical structure using silicon. And this is the curve stress versus strain. If you increase stress, it will just follow a straight line path, and strain will means elongation will be there in a particular direction. So, this is the stress strain curve, and so long it is linear it is used, and as it becomes nonlinearity, so then it some other deformation takes place basically. In this case, so long it is linear, if you reduce the stress, strain also will be reduced. Okay. So, that is we expect there should not be any hysteresis also. Stress strain curve, this linear region is used for making micro mechanical devices or sensors. Now, the Young's modulus and elastic modulus is basically stress by strain. I have shown it sigma divided by epsilon, and there are two kinds of stress. One is known as a tensile stress, which is positive in nature, others is a compressive stress, which is negative in nature. Compressive stress we call it negative stress, and tensile stress we call it as a positive stress. Okay. And the higher the E means the Young's modulus or the elastic modulus, the less the material deforms, because E value is more, the deformation will be less. E is anisotropic in nature, is very important, and a function of crystal direction. That E means Young's modulus or elastic modulus is anisotropic, that means in different crystal oriented direction, crystal plane value is different, it is not same, and that property may be used to make certain sensors for certain applications. So, other is the shear stress and shear strain. So, let us see in this picture how can we define shear stress. For example, this is a block, and in that block force is applied parallel to a surface. In other case, we have shown axial force is applied perpendicular to a surface. Now, this is a body. Now, this lower part of the body is fixed. So, upper part of the this body you have applied a force in this direction, parallel to this surface you are applying. So, there what happens, the top plane is deformed or bottom is fixed. Initially it was in this shape. So, later on if you apply force at the top of this surface, so it bends in this direction, dotted line is the new position. So, what is the change delta x? Delta x is the change in this direction in which you have applied the force. Now, here this displacement delta x divided by L, the one side of this particular object, the delta x the displacement by applying force F at the surface divided by L is known as the shear strain, that is by gamma, and shear stress is again force per unit area, Newton per meter square, that is the tau. Okay. So, shear stress is tau, Newton per meter square force per unit area, and shear strain gamma is delta x by L. So, displacement is delta x on this surface. Okay. Now, the modulus of shear modulus of elasticity, other you have seen the Young's modulus in case of axial stress and strain. So, here you will have shear stress and strain, shear modulus or shear modulus of elasticity. So, that is known as a G. G is again stress by strain, which is tau divided by gamma in case of shear. So, the higher the E, the less the material deforms, like the axial stress. Another important point, for isotropic materials, E equal to G. What is E? E is elastic stress and G is shear stress. Elastic modulus or this shear modulus. So, elastic modulus and shear modulus will be equal for isotropic materials. Okay. And some of the materials are cited here, which are used in case of the microsensors. Here you can see the ceramic is there, some case of metals are also there, for example aluminum, molybdenum, stainless steel, tungsten, steel, these are these belong to the metallic group, and Young's modulus is a gigapascal, that is 210, 410, 200, 343, something like that. Silicon is 190, and ceramic materials are also there, aluminum oxide, silicon nitride, silicon dioxide, these, and diamond is a maximum Young's modulus 1035. Okay. So, these are the values of the Young's modulus in for certain materials. Now, the Poissons ratio is another important parameter which is required for the analysis of the mechanical or the stress strain analysis of silicon for mechanical microsensors is required. So, this Poissons ratio is when an axial tensile stress is applied, the diameter decreases. With an application of the axial compressive stress, the diameter increases. So, when I define the axial, then I told you the diameter is not changed, only along the length change, but in reality is not the fact. So, if you elongate a body, diameter will shrink, is not it? That is the actual reality. So, there the diameter decreases if you apply tensile stress. For on the other hand, if you apply compressive stress, the diameter increases. So, the axial strain is a EA delta L by L we defined earlier. There is a transverse strain, that is a epsilon T, which is a delta D by D. So, delta D by D was not there when I defined the axial. We assumed that time that the diameter no change, but if it also changes, it is shown in this diagram. You see the length changes in this direction, and diameter from here also it is reducing. So, you see this is the D minus delta D, and total say diameter is a D in this length. So, D to D minus delta D, so change is the delta D. So, if you take delta D divided by D, so that is known as a transverse strain, or it is known as epsilon T. Okay. And earlier the axial strain is epsilon A, which is the elastic Young's modulus or elastic modulus I defined earlier. So, now the ratio of epsilon T by epsilon A is Poisson's ratio. Poisson's ratio is epsilon T divided by epsilon A, that means transverse strain divided by axial strain is the Poisson's ratio. Now, here in ideal case, when there is no transverse deformation, obviously epsilon T equal to 0, then we will have only epsilon A, and then epsilon A in that case we can call it a nu, and it varies from 0.1 to 0.5. Okay. For isotropic material, where E is equal to G, and that is an ideal condition, but normally we have seen that E and G follows certain relation, and that is E equal to twice G into 1 plus nu, or 3 K into 1 minus twice nu, where K is the bulk modulus for volume compression. Okay. K is the bulk modulus for volume compression. E is here the Young's or elastic modulus, G is shear modulus, and nu is the Poisson's ratio. So, these are the different parameters which we should know before designing certain mechanical structure or mechanical micro sensor. Now, another two parameter we should know, that is yield and tensile strength. Yield and tensile strength. So, stress strain curve is shown here, you see stress versus strain. So, initially it is a parallel, initially it is straight line nature. So, up to this P point it is a straight line nature. So, that way here I can say the strain and stress are proportional, is exactly linear. Okay. Now, after a certain point you see the curve is not linear, it is becoming non-linear. So, now after if you go on increasing the strain, then we find it reaches a maximum point of stress here, then again it falls, the curve goes down. Okay. That means the left side of this point P, where the linear nature of the stress strain relation is valid, this region is known as the elastic region. That means, their material is elastic behavior is maintained, but as soon as you exceed the point P, the behavior is a plastic behavior. So, there is a difference between elastic and plastic. So, in elastic means stress strain relations are linear, plastic means stress stress relation is nonlinear. So, there deformation takes place and this deformation leads to the permanent deformation. In this part up to point P, so if you release this stress, so it can go back to its original position, that is the elastic property. So, if you release this stress, so it will go back to its original shape, that is the elastic property. But after that, after certain value of the stress, so it cannot go back to its original shape. So, that is the permanent deformation. So, this permanent deformation will go on up to certain point. So, after that the material the stress, if it reaches a certain point, then the material will break. So, that is why you are getting the curve just it goes down. So, that means with this respect there are two other definition, one is known as yield strength, another known as tensile strength. What are those definition? You can see here the sigma y, which is a yield strength, is the stress above which the material will permanently deform, which is known as plastic deformation. So, that is this point, you see this from here to here is a plastic deformation and that is known as permanently deform. Sigma y may be determined by the 0.002 strain offset method, that is a 0.002 strain offset, certain technique is there by which you can determine the value of sigma y. On the other hand, the tensile strength sigma t is the stress above which the material will completely break, that is the tensile strength. So, that means yield strength basically material deform and that deformation is a permanent deformation, but in tensile strength means their material breaks. These are the difference between yield strength and tensile strength. Basically strength means you are applying stress. So, when you are working for certain sensor, you have to be cautious. So, you should not apply stress, so that the yield strength or tensile strength it reaches. So, yield strength is higher is preferred always, is not it, so that you can use maximum amount of stress. So, you look for material whose yield strength is higher. Okay. So, I will at the end of this lecture I will show you certain table which gives the yield strength value and tensile strength values of different metals and semiconductors and other ceramic materials also. Now, the yield and tensile strength sigma y and sigma t, when the sigma t is greater than sigma y, the material bends before breaks, is known as a ductile. So, ductile or brittle, these two words is also used, one is ductile, another is a brittle. What do you mean by ductile? Ductile is sigma t is large compared to the sigma y, then material bends before breaks. This property is known as ductile property. On the other hand, when sigma t and sigma y are comparable, then material breaks and it is a brittle material we call it. Maximum point of the shear stress strain curve at which fracture could result. So, I have shown you last diagram where the maximum value, after that the material breaks brittle. Okay. So, these are the mechanical properties which are which you should know before going for design of any micromechanical structures. So, now the other mechanical properties are also important when you go for designing any MEMS devices. These are thermal expansion, hardness. What do you mean by the thermal expansion is known to you. Thermal expansion coefficient is known as alpha and it is basically delta L by L by K, K is in basically the temperature in absolute scale. So, it is defined percent change in length per unit K. So, that is thermal expansion coefficient, you should know it. It results in thermal stresses due to mismatch in alpha between different materials. So, you see thermal stress, earlier stresses we discussed, that is the mechanical stress, that we are applying certain mechanical force and as a result of that force means that strain will be developed inside the material. So, another stress is also there, that is the thermal stress. That means, if in a sensor you are not going to make the sensor using only single material, and you are using different kinds of material, semiconductor, ceramic, metals and so on. So, all the material will not have the same thermal expansion coefficient. So, if the temperature changes, the operation temperature, because you are using sensor not in a fixed temperature, at different temperature range you are using the sensor. So, in that temperature range the thermal expansion coefficient is not same, and as a result of which there will be a stress, and that stress is known as thermal stress. And because of that stress, some of the sensor behavior or sensor output may also change. So, that also you have to keep in mind. So, other than the mechanical stress, another stress is also involved, which is known as the thermal stress. Hardness is another mechanical property. Physical hardness of a material characterized by Krupp hardness constant, and it is in kg per millimeter square. Krupp is basically the name of a scientist. He investigated that particular property of that material, that is why it is characterized by Krupp hardness, and it is defined by kg per millimeter square, its unit. Now, others are creep and fatigue. These are all mechanical properties. What is a creep? Creep is basically it is a time dependent and permanent deformation of materials when subjected to a constant load and stress below or close to the yield strength. It occurs at elevated temperature and static stress. If temperature is elevated and a static stress is applied, then this is known as the creep. Okay? And other property is known as the fatigue. What is fatigue? Change in material properties caused by cyclic loads or stresses much lower than yield strength. That means, you are applying stress lower than the yield strength, okay. But if you are applying cyclic stress, that means once you are applying stress then releases, again you are applying stress then releases, again you are applying stress then releases. In a cyclic way, if you apply stress and then release, then the material property, that particular mechanical property of the material will little bit change, and that is known as the fatigue, as if the material reached its fatigue condition. It may not follow the linear stress strain relation. So, that is the fatigue. Okay. So, these are various kinds of the mechanical properties, the axial stress, shear stress, the yield strength, brittle, ductile, creep, fatigue. These are the various kinds of mechanical properties one should take care of when you are going for design of any microstructure using silicon or any other single crystal, or even using the metal or metal alloys. So, let me stop here today. So, next class I will discuss on the different properties of the materials which are used for making microsensors and MEMS devices. Thank you very much. Yesterday we have discussed on the MEMS materials. So, different types of materials which are used for making microsensors and microsystems. Today we will discuss on the properties of the materials which are used for microsensors, MEMS and microsystems. Different kinds of properties of the materials are used for making sensors and actuators, and those properties one by one we will discuss in today's lecture. So, now first I will start from the silicon, because in the last class we have seen that different kinds of materials other than silicon also are used in MEMS. They may be ceramics, they may be polymer, they may be composite materials. but among the semiconductor materials, silicon is the choicest material for MEMS because of various reasons, and those reasons one by one we will discuss now in today's lecture. So, silicon is a mechanical material and which is having single crystal, and it has got diamond crystal structure. Its density we have seen is equal to aluminum, nearly equal to aluminum, but 1/3 of the steel. So, in that respect the silicon is lighter than steel. In the second point, it hardness. Hardness half of steel and greater than iron, tungsten and aluminum. So, so far as hardness is concerned, the silicon hardness is greater than the iron, tungsten and aluminum. Thermal expansion coefficient is a half of steel. That is a good thing, that is thermal expansion coefficient is not very high. So, now other properties are yield strength 2 times greater than steel, Young's modulus is almost equal to steel, thermal conductivity, that is 1.5 times of steel, deformed elasticity, and remember not plasticity. Difference between elasticity and plasticity has been discussed in last lecture. So, the deformed elasticity and it has no hysteresis. So, silicon and its derivatives, particularly silicon dioxide and silicon nitride, are some of the best electrically characterized materials in the world. So, in different MEMS structure, we take help of these derivatives of silicon, that is silicon nitride and silicon dioxide, and their properties and their characteristics are well known to us. That is one of the advantage in case of silicon. So, other things are mentioned here in favor of silicon, that is it has got excellent mechanical performance and it enables effectively to replace a majority of all other sensing technologies. The existing infrastructure of the mainstream IC industry is available. So, that we will use in case of MEMS fabrication or microsensor fabrication. So, that is why it is very easy to develop products which offer an unmatched price to performance ratio. Performance will be very good and price will be low. So, the ratio price to performance is extremely low in case of silicon because of the availability of the infrastructure, which is very important. If you have to create new infrastructure, then obviously the price to performance ratio will be higher and higher. So, since it is available, so that ratio will be extremely low, that is advantageous for commercial production. So, that is one advantage in case of silicon. The other one is this particular things is based on known characterization of silicon. It can be classified as the best material for mechanical sensors. Silicon mechanical strength is comparable to even higher than steel, but at a lower density and better thermal conductivity. In the last slide I show you its density is lower than iron and its thermal conductivity also very high, compared to 1.5 times of that. So, because of that it cannot generate lot of heat, dissipation is more, and that is advantageous compared to other material of the traction. So, then it has plus delta is shifted upwards. So, plus delta if is shifting upwards, then what will happen? So, in the traction axis, so the gap energy, if delta is shift upward, so the band gap increases. So, because of the band gap increase, so what will happen? So, less number of carriers will have the probability to jump into that level conduction band, because delta E energy band gap has increased. So, probability of jumping that higher gap will less. Okay. But on the other hand, if you apply a compression axis which is 100, so there you see the band edge of the the Fermi level, the band edge reduces by minus delta E. So, that means here there is a probability of the carrier should be more here. So, that means if you apply the traction axis that we elongate there is a probability of movement of the carrier from this axis to this axis, because here easily they can jump, but here no, here increase. So, the mobility of the carriers may increase, because there is a tendency of movement of the carrier along this compression axis. So, as a result of which here mobility will increase. Mobility increase means piezo resistance will decrease, conductivity will increase, but here the opposite. So, these are the explanation of the quantum physical explanation of the piezo resistance effect. Now, there are certain points. This model is known as many valley model. What I explained is narrated in this few points, which you may go through. So, anisotropic stress condition changes the relative energies, and hence the population in these valleys. Why I just explained why the population will increase. Traction in a valley direction removes electrons from the valley and transfers them to valleys lying normal to the traction. Normal to the traction is the compressive, this 100 that I explained. Compression has the opposite effect. Okay. The energy decrease minus delta E in 100 helps more electron to enter in the conduction band, minus delta E helps more electron in the conduction band. In 010 direction, the minimum required energy increases by delta E, that is shown in the last view graph, and less electron satisfy this condition. Okay. Other points are, thus average mobility becomes lower in the direction of traction, which is longitudinal effect, and higher in the direction of the transverse to the traction axis, which is known as the transverse effect. The more the trace in the lattice destroys the symmetry of the valley structure, the larger the piezoresistance effect produced. Another observation. Third observation is, in n-type silicon, the valleys are aligned to 100 axis, and the trace in this direction significantly disturbs the symmetry, and so pi 11 is the largest coefficient for n-type silicon. There is a reason why for n-type silicon pi 11 is the largest. Other hand, for p-type silicon pi 12 and pi 11 will be higher than that, pi 44. So, that is because of this reason. For p-type silicon, many valley model is found to be less accurate. Doping concentration in n silicon should not be chosen too high in order to keep a reasonably high gauge factor. Other comment, many valley model predicts a decrease of the piezoresistance effect with increasing temperature because of inter-valley scattering. So, with temperature there is a inter-valley scattering. So, because of the scattering increases, it predicts decrease of the piezoresistance effect. Okay. So, these are the few points on quantum physical explanation. So, I will stop today. Next class I will continue with the properties of the MEMS materials, which are mainly I will discuss the piezoelectric effect and piezo the thermal effect. So, all those effects will be discussed in the next class. Thank you very much.